It's been 30,000 years, but you are back. It is Coach Botzer. Okay, so you don't need this for the AP Physics C E&M test or the mechanics test. But what we're about to talk about are Rlc circuits, also thought of as a damped harmonic oscillator. And while we're not going to talk about these in high school, you don't need to know how to do this math or anything. If you're looking back years later on these wonderful videos from college, you're definitely going to have to do them there. But the real thing that you need to know how to do in order to solve these type of circuits or damped harmonic oscillators out is you need to know ordinary differential equations, or ODEs. And specifically in the case of an RLC or a damped harmonic oscillator, you're going to need to know how to solve a second order diffie-q. Okay? You won't know how to do that until you take your differential equations course. So we're not going to get into that large pit of mathematics that goes into that, but we're going to show you here what a normal LC circuit looks like, what an RLC circuit looks like, how we'll set up the Kirchhoff loop, and then just what is the final answer that you will get out of it. How you prove you get that answer? Well, that's on you. Use your differential equation knowledge. We're not going to do that here, okay? So let's just start with this. We know that our LC circuit is going to create for us a harmonic oscillator. And when this circuit is going here, the circuit is going to oscillate in a nice sinusoidal pattern, okay? And that's actually kind of weird. I'm kind of drifting on that one, didn't I? Nice sinusoidal pattern. There, that's much better, okay? Or, maybe that's going down a little bit, whatever. On this sinusoidal pattern here, let's just move that up, make that a little bit better. Cool. This amplitude is going to stay the same the entire time. Okay, we're not losing any amplitude. And our periodicity, 1 period, 2 period, the 3 period about here, will be the same the entire time. For a damped harmonic oscillator, though, something like a RLC circuit or like a block spring but with friction on the table, what we're going to see is something a little bit different. What we're going to see is the same kind of sinusoidal up and downs that we have, but they're going to start, whoops, this is hard to draw on the computer. It's much easier to draw on paper. They're going to start at high amplitudes, and then that amplitude will be decreasing as time moves on. It'll actually be a curve at which these amplitudes fall off on. This is a damped system. Okay, it is a system that is going to lose some energy and as a result some amplitude with time. This curve right here, this is actually an exponential decay. Okay, this is a decay here. And typically these go, well, for an RLC circuit, it's going to go as e to the negative RT over 2L, where R is your resistance, L is your inductance. Okay, that is the rate of decay that this will die off on. It'll never get to zero. You'll still see small oscillations here at infinity, but it will become arbitrarily close to that as time approaches infinity. But that is the decay. Other than that, it's still going to have the same period here. Note that, we have peak, we have, well, poorly drawn, but the peaks, distance between them are staying the same. It's just that this amplitude is crashing down on us. And the reason why this amplitude is crashing down on us has to do with how we think about the Kirchhoff loop. We already knew that if we just had a LC circuit, so here's what we had in the past, and if you haven't watched this video yet, go check out LC circuits and the equations there. But we saw in our LC circuit that if we had Q over C plus, and it was a very careful measure that this is a plus here, plus LQ double dot, this is di dt right there if you have forgotten that, this will equal 0. And because of this, we were able to see that this is a harmonic oscillator. If we toss in a resistor here, this equation changes somewhat. This equation will also have to it a plus IR term equals 0. Okay? Now, this I we could think of as Q dot, like that. And when we do this, we now have an equation that looks like this. We have LQ double dot plus QR plus Q over C equals 0. Because this is, we have the second derivative, we have the first derivative, and we have the original function itself of this. This is a second order differential equation. These are tricky to solve, okay? If you are solving it, what you will get as an answer here is you will find that Q of t, so the charge on the capacitor as a function of time, is equal to the maximum amount of charge the capacitor could ever have times, and then here's your exponential decay, e to the negative, and then this was the RT over 2L. And then we multiply this by cosine of omega prime t plus phi, where this omega prime is actually equal to something else. This omega prime here is equal to the square root of omega squared minus r over 2L squared. Okay? If for some reason your omega prime is less than omega, because like you have a small value of r, it's a very small resistance, then essentially what you can say is that omega is just approximately equal to 1 over the square root of LC here, which you already knew that because let's say r was so small it was 0. That's what we found for just the LC oscillator, because we have the resistance here that changes slightly for our angular velocity. So this is what the equation will be for this differential equation, the second order differential equation, if you go ahead and solve it. Like I said, they're a little tricky to solve, but you'll see how to do it in your differential equations courses. And basically all that it's saying here is, look, we're still going to get a harmonic oscillator, something that's going up and down due to that cosine term, but it's going to decay here from this exponential decay that's happening. Okay, so it's a kind of neat thing that occurs, and that's for every damped harmonic oscillator. The thing that will change between, a mass spring or a pendulum as it's going down, or this RLC circuit, is what's going to be up here in your exponential decay, and then what are you going to have in here for this. Notice how the r over 2L and the r over 2L are very similar here. The exponential decay just takes place with time. So this is just this damping term that matters here. And you'll see that depending on your damping term, you can have an over-damped system or a under-damped system. But that gets into like some really more advanced stuff as we go along here. Okay. But this is the setup here on what's going on. Every once in a while, people ask, hey, Coach Botzer, how did you get a positive here? Because I thought for a Kirchhoff loop, we normally had minus IR for that, because that's I and that's R. The reason being is if you think about Kirchhoff loops as a function of energy, you can say here that because you have some thermal energy lost, the change in thermal energy as a function of time is going to be equal to this IR term here, and it's technically a negative term here. That also has to be equal to L di dt plus the Q over C. So this actually gets added in there, and that's why you get a positive there. So that's what's going on in this case as we're kind of going through this. So nothing too crazy that's happening. If you're looking at this in a book and you're like, hey, why does a textbook have an extra I term throughout all of this? I divided an I term out because I'm taking that derivative of the function time anyways, and it's going to go away. Okay. Really, I just think listen to your Kirchhoff loop and just recognize that they all need to be positive, and you'll be good on that. And then, know your differential equations. But like I said, you don't need this for the AP Physics C test for mechanics or E&M. It's just a neat thing I wanted to show you. You'll see a lot more of this in your collegiate career whenever you start doing your differential equations and moving into this kind of stuff. Okay. But for right now, this is finished. Adios. Take it easy. And make sure at this point, if you've gone through all the AP Physics E&M videos and all the AP Physics C calculus-based E&M stuff, and you're prepping for the test, it's time to just work on practice problems. It's time to just open up 1,000 free response questions and churn them out like there's no tomorrow. We've already got a bunch made on this channel if you wanted to see how they go. So start Googling those questions, start answering them, and then follow along to see how we solve them here. But until next time, adios, and take it easy.